So I'm going to start off with an overview of the topics that we covered, some of the important topics that we covered in the first webinar. I'm also going to give you an overview of two example bridges, the Shanders River Bridge and the Peace Bridge. So I'll talk about the layout and the number of girders, spacing, etc. for these two structures. I have my co-presenter today, Andres from Sophistic. He has very kindly taken on this task of presenting with me today. So he will be describing, using Sophistic, which is an amazing parametric software. He will be describing the parametric concept for bridges. He will start with parametric modeling using Sophie Plus. This is the AutoCAD-based preprocessor. Similarly, he'll talk about parametric modeling using Grasshopper, which is a visual programming based on Rhinoceros 3D tool. Then he will describe a bit of an overview, or give a bit of an overview about analysis options. This will include stick, hybrid, and full 3D finite element modeling. And once we've had a bit of an intro to these topics, he will be demonstrating through real examples, which are the Shanders River Bridge. That is a single span bridge, as well as Peace Bridge, which is a two-span continuous bridge, the principles that we want to convey to you. So we will be seeing some very good discussion about simplified analysis using the stick model. This is where we use the distribution factor approach. Andres will be talking about that and showing us how to model. This is pretty simple. And then he will be showing the refined analysis using the hybrid model. That will be done for example 1 for Shanders River Bridge. And then example 2, Peace River, will have, again, two different modeling and analysis techniques here. We'll be using the refined analysis for this case. We'll be using the hybrid modeling as well as full 3D modeling. So Shanders and Peace bridges are fully developed examples from our course, which is giving you a really good amount of information on context-sensitive conceptual bridge design. This is course number 3 of the series. It's titled Training in Step-by-Step Development of Site-Specific Bridge Solutions. This is where we show you some real engineering of two constrained sites. The sites are highly constrained. One site is driven by hydraulic considerations, while the other site is driven by seismic considerations. What we do in there is produce several constraint compliant solutions. So all the solutions we come up with for each site are constraint compliant. They follow all the constraints that are imposed or present in the site. And then we show you different ways of how to arrive at the best possible solution out of the developed ones. So the first one is a design bid build project, which is a more typical delivery, and the second one is a design build project, or part of an alternative delivery, so you get to see the differences in the process and the outcomes and the deliverables between the two. So if you're really interested in propelling your career forward, this is how real engineering is done in an office, and I would really recommend that you take an opportunity to have a look on our website and see if this is something that you would like to get your hands on. Okay, moving forward, and just as an introduction, what we had discussed was that fatigue is the initiation and propagation of microscopic cracks into macro cracks that occur under repeated stress application. And metals such as steel, aluminum, etc. have a high propensity to start cracking because they have imperfections in stress concentrations during the production and fabrication processes. The fabrication and structural design have to endeavor to avoid all processes and details that would be prone to crack induction while things are being produced or fabricated. However, what we find in practice is that it is impossible to completely preclude cracks and inclusions, internal discontinuities, etc. when we are fabricating metallic elements. So this course, or this discussion, is really limited to steel bridge elements, and that's why we're really going to be focusing on fabricated steel elements. What we find is that the repetitive loads that come onto our structure do not have to have magnitudes that cause stressing levels that are much smaller or that are comparable to the yield level or higher. In fact, this phenomenon takes place even when the stress levels are much smaller than the yield stress of metal, and the growth of cracks can still occur. Okay, so the most common civil structures that must be given due fatigue considerations are bridges, and that's what we're talking about here. Some steel structures that are not bridges, such as sign structures that are actually present on bridges, may be governed by wind loads for fatigue. But bridges, for the most part, they only need consideration of live load stresses that are induced by trucks that frequent the bridge. They're not driven by the wind loading or temperature loading. And the reason for this is that the loading that's induced by trucks far exceeds the service wind load on the bridge superstructures. And therefore, we really just ignore that, except for when we have sign structures that are quite flexible. And that's when the wind can excite vibrations in them. And with a lot of wind cycles, you can actually start to fatigue these sign structures. The way things happen is that for bridges, for metals, we have crack growth in metals that occurs due to the presence of two conditions. These are existing flaws and tensile stresses. So if you didn't have any flaws or no tensile stresses, or neither, then you would not be running into this fatigue problem. But we know that the existing flaws are always there, and the bridges under service see tensile stresses due to the passage of trucks. Really, we can divide the crack growth into three distinct regions, which is initiation, stable propagation or growth, and unstable growth that leads to fracture. For bridges, really the crack initiation is simply ignored because we have found that that little bit of an initiation is already there as a result of the fabrication process. So our designs are really based in this regime, which is the stable growth regime. So the crack propagation regime is right here. It has a portion within the stable growth regime, and after you hit a certain critical flaw size, then it takes off on us, and it leads to fracture after some unstable growth. So this is a graph where you have some initial flaw size and the number of fatigue cycles or stress cycles on the right hand side, and here is the publication from which this figure has been adapted. Generally speaking, we have two types of fatigue: the load-induced fatigue and the distortion-induced fatigue. The load-induced fatigue basically occurs due to primary or in-plane stresses in the steel plates that comprise or make up the steel cross-section of the bridge elements. So this is really straight up in-plane stresses that occur because of the live load. And the other source of fatigue is distortion-induced fatigue. This type of fatigue occurs due to secondary or out-of-plane effects on the steel plate. So this is when transverse members basically make the primary longitudinal members bend out of plane. We are going to be shedding a lot more light on this one in the third webinar that's going to be coming up next week. So for sound bridge practice, we have to have both types of fatigue that need to be discussed and designed for. Otherwise, we will not be getting the intended performance from the bridge throughout its lifetime. So we have to look at both load-induced and distortion-induced fatigue. This is really analyzed for, and stresses are calculated. It's very difficult to determine the stresses due to distortion-induced fatigue, and what we really do is we detail in a manner that just prevents distortion in the steel elements to keep the distortion influencing the fatigue life. And the distortion stresses are basically just either very low or entirely absent. Okay, when we look at load-induced fatigue, what we find is that modern codes such as AASHTO, CSAS6, EC8, they do not typically require the determination of residual or peak stresses. What we do is we really work with nominal in-plane stress values, and we can determine those using ordinary elastic analysis and mechanics of material principles. So, for example, in a negative bending zone for this composite steel girder with that's composite with a deck, what we would do is, for looking at the top flange, we would simply divide the live load by the section modulus at the top to get our nominal stress. Okay, now when it comes to the load-induced fatigue stress, here is a typical SN curve where we have a stress proxy, which is usually a nominal stress or the nominal stress, and here we have the number of stress cycles. You can see as the stress on the fatigue category or the fatigue detail goes down, the number of cycles or the fatigue life goes up. So the fatigue life of a particular detail is really given by this SN curve, which provides information about the allowable fatigue life. In a nutshell, what we have is the fatigue life determination in terms of the number of cycles based on the nominal stress level that's experienced by a detail under consideration. So that's what we really do. We calculate the number of stress cycles on a detail, and we calculate the nominal stress, and that's how most of the modern codes are calibrated for new design. I've already kind of described this. So what happens is that the number of allowable cycles is a function of the detail type. In AASHTO and S6-19, the detail types are A, B, B prime, C, C prime, D, E, E primed, etc. in AASHTO, and A, B, B1, C, C1, D, E, E1, etc. Okay, so they're exactly the same, but the symbols may be a little bit different for some of them. Just showing one fatigue category here, which is B, and this is an example where we have continuous fillet welds that are parallel to the direction of applied stress. So if this is a built-up steel member, a steel girder, for example, and you apply bending on it, then you have your stresses that are aligned in this direction, and you can see that that's the axis of the weld as well. So the fatigue stress is parallel to the weld, and that's considered to be a fatigue category B detail. What we have to do in load-induced fatigue is figure out the nominal stress value that corresponds to the cyclic stress range due to truck passage. So it's not just the one cycle, you have to go to the other side. For example, if this is our location of interest, when we put the load on this remote span, then we see a reversal in stress. So what this figure is showing here very quickly is this is the dead load tensile stress at this location. The truck comes along, and when the truck is on the span where we have the location of interest, we get a positive peak. But when it's on the other side, we get a stress which in itself is tensile, or I'm sorry, is compressive in nature, but it's still lower than its magnitude is lower than the magnitude of the dead load tensile stress. So overall, you're still on the positive side, so you're still in the tensile zone, and therefore the stress range, which is a tensile stress range for design, has to be taken as the maximum live load stress minus the minimum live load stress. So our stress range that the design is going to be based on is going to be this value and not this value. Okay, we have different load combinations and factors in AASHTO versus S6-19. S6 has just a single factor, which is 1.0 L. It's really shown as 1.0 D plus 1.0 E plus 1.0 P plus 1.0 L, and we had discussed this. This gives us the permanent stress. Really what we're after is this stress. And the reason why we need to at least look at this is because of what I'm showing here. If this stress were to go below the negative side, our stress range would stay within this zone. We would cut it off here because we are only looking at a tensile stress range. The only way we can find out if the overall stress has reversed from tension to compression is if we have a handle on the permanent stress state, and that's why it shows up as this. But for most cases, you're really just looking at the tensile stress range for the live load. When we go to AASHTO, we have two load combinations. Here you have the live load plus the impact and the centrifugal force, and it goes without saying that it's the same over here. The difference is that here the factor is 1.0, but we have to look at impact, and if it's a curved bridge, we would be looking at centrifugal force. But here our factor is 1.75 for the infinite load-induced fatigue life. This is the FLS combination 1, and then we have the FLS combination 2, where we're looking at a finite fatigue life check. We only carry this check out if the first check is not satisfied, and here the load factor is 0.8. Really looking at AASHTO, the limit state function looks like this. This is the load factor, this is the nominal stress, including the dynamic load allowance, and it has to be under a certain value. So this is the capacity side, and this is the demand side of the function. Okay, so delta F is the stress range based on the nominal stress for the detail that we have, and delta Fn is the allowable stress range. For FLS1, it is given by the constant amplitude fatigue threshold, which we know is a threshold below which you will get an infinite number of cycles if the amplitude of the cycles is the same. But we know that that is not the case. So this is only used when we have a infinite fatigue check. And that's where you see that in order to account for the fact that this value can actually vary quite a bit, our factor is quite high. On the demand side, we have a pretty high factor. For FLS2, the delta Fn instead of being delta Fth is given by this formula, where A is a fatigue constant and N is the total number of cycles in or on the detail. When we go to the S6, we have something that is similar. So here's the nominal stress, here's the stress capacity on the right hand side. CL is a factor which basically accounts for if the loading is higher than the design truck loading, which is CL 625 in S6-19, that's the truck. In AASHTO, it's HL 93. And here we have a truck calibration factor of 0.52. So what this does is it gives you the average truck. The design truck is quite heavy, and the code has done calibration and found out that most of the fatigue damage would come about not because of the really heavy design truck, but something that's on average about 52% of the truck that we use for design. So that's where this calibration factor comes from. The one thing that I had pointed out in the last discussion, where we have a bit of a difference between AASHTO and S6, is the slope of the SN curve. For AASHTO, it's a straight line at 1/3, but in S6-19, at this FSRT, which is nothing but the constant amplitude fatigue threshold per AASHTO, it's called FSRT per S6-19. We have the line that changes, the SN line changes its slope from 1/3 to 1/5, and this is more in line with the Eurocode, and this is a figure out of the Eurocode. So if we are below this threshold, then we can have an infinite life per S6-19 as well if certain conditions are satisfied. But we have to compare it with the slope line with the line having a slope of 1/5. So here this gamma is simply A per AASHTO and NC is N. So here we see that FSR would be the same value as per AASHTO as long as this value is below FSRT. However, if that's not the case, then this value will be a different fatigue constant gamma primed over NC to the power of 1/5. And if this number happens to be lower than half of the FSRT, then you just cap it at this value. You don't need to go below that. And the whole idea here is that S6-19 manipulates the demand side of things by a factor of 2, whereas AASHTO manipulates the, let me repeat that, S6-19 manipulates the capacity side of things by a factor of 2, whereas AASHTO manipulates the demand side of things by a factor of about 1.75. In fact, if you were to look at the load factors between AASHTO and FLS1 and AASHTO FLS2, they're 1.75 and 0.8, and this is actually a bit larger than 2.0. So really that comes from the realization that the constant amplitude fatigue value could vary by a factor of about 2, that stress can vary quite a bit. Okay, we talked a little bit about simplified analysis. Really, in this case, we make a line model, and then we have a distribution factor that we calculate based on the code. We multiply that with the global value that we get from the truck to get the individual girder demand. So for refined analysis, we can run these when we do not have the conditions that we do not have a bridge that satisfies conditions for simplified analysis. So both AASHTO and S6-19 give us various conditions under which the simplified analysis can be used to determine girder or component demands, basically using a one truck on a line model. But when those conditions are not met, then we go to refined analysis such as grillage, finite element, etc. Per AASHTO, we are going to be employing refined analysis, or when we employ refined analysis, we'll be using a single truck, and we have to position it transversely and longitudinally so that the stress range at the detail under consideration is maximized. AASHTO has this consideration irrespective of the position of traffic or design lanes on the deck. So I'll show you a couple of cartoons in just a minute, and this will become more clear. In S6-19, the truck has to be placed in the center of the travel lane, of one travel lane. So really here, you can see per AASHTO, when we're looking at the exterior girder fatigue, we would push the truck in a position that is the worst position longitudinally, but also transversely, say, for example, for the exterior girder. So even though your painted line might be here and the lane might be here, we're not going to center the truck here. We would push it all the way to the worst position so that this girder sees the maximum demand. Similarly, for the demand on one of the typical interior girders, we would push it towards the center regardless of where the lanes are. We have no consideration of the lanes. We would just place the wheels so that the position gives us the worst demand. According to AASHTO, it would be appropriate to place the truck in the center of the lane if the traffic lane position were fixed, and we knew that this would stay the same throughout the bridge service life. However, we know there is uncertainty in the future traffic patterns, so we minimize these in order to minimize our calculations and to get us the worst demands. AASHTO makes this irrelevant. It makes it regardless of what the pattern is and where the painted lines are. S6-19 is a little bit different. What we have to do is position the truck for fatigue demand for at the middle of a travel lane. And here, again, you may have 3 lanes that are painted, but what we have to do is look at the clear width that's between the barriers, and we have to divide it by a value n, which is the number of design lanes that's given by table 3.5 in the code. And this works with the clear width, or the clear width of the bridge, and it tells you if your bridge width is between so many meters to so many meters, your number of design lanes is this much. So once you have that, then you basically come up with the effective number of lanes. Once you have the effective number of lanes, it doesn't matter where your painted lines are, you're going to have that many number of lanes on the bridge. So you may have only 2 painted lines, but if your number of lanes, design lanes per the code is 3, then you're going to have to divide it into 3. But then you will place the truck in the middle of a given lane to get the maximum demand for a given girder. So this is showing a case where you have 2 lanes, 2 effective lanes, so the center line of the truck is aligned with the center line of the lane. Okay, just very quickly, these are the 2 examples. The Shanders River Bridge. This is one of the sites that we're discussing later on, and Andres is going to show you stuff with this. So the main span here is 58 meters. That clears the Shanders River, but then to get to the appropriate locations, we've got 6-meter jump span. So this is a simply supported single span bridge as shown here. We've picked up the steel option obviously for this case, and this is just these are just a few cross sections, the bent cross section as well as the abutment cross section, but here is the cross section of the deck. So this has got 4 girders, 3 spaces at 3.4 meters for a total width of 12.78, and the sizes for the top flange, the web, and the bottom flange are given right here. The second one is the Peace Bridge, and this is a 2-span continuous structure with two 49.3 meter spans, continuous spans, again, some cross sections. Here we're showing 6, but later on this example got refined to only five girders, so that's what Andreas has run his analysis on. So these are extended pipe pile bends where the pipes stay about a meter, meter and a half in the ground, and then you have the reinforced concrete column coming up, you've got a cap, and then you've got 5 girders sitting here, and they're at 3.6 meters each. Okay, so, and here we're just showing the different sections that were taken, and then we developed the example in the course and also taking it in this one. And when we go to the next talk next week, I'm going to be describing the some of the fatigue design issues or the fatigue design steps for this particular structure.